Allora vi invito a tornare tutti in aula, per favore acceleriamo il rientro, la ricreazione è finita, ricominciamo con i nostri keynote speeches di questo Quant 2026, tra poco anche la premiazione del contest che abbiamo visto prima, lo Shark Tank, e iniziamo subito da una presentazione che è quella di Gabriele Susinno, che è Senior Client Portfolio Manager di Pictet, che invito a raggiungermi sul palco, è dedicata a Econophysics, cioè come integrare la fisica nel portfolio management. Le presentazioni continueranno ancora in inglese, quindi benvenuto e lascio il palco.
Grazie. Grazie mille. Buongiorno. Shall I speak English? Yes, I think so. Yeah. So, you may have seen in the previous presentations, particularly the one from Allianz, how many physicists and mathematicians belong to groups that works in finance. And often, because half of my professional life has been devoted to astrophysics and particle physics, and the other half to finance, people tell me, but what's someone like you that was hunting exoplanet is now doing in finance? But because we have a lot of things in common in finance. And actually, I started in physics, from telescope to particle detectors and statistical noise. Today I work in finance. Sorry? Oh, now it's better. Oh. So I was saying that I started in physics, working with telescope, particle detectors, and statistical noise. Today, I work in economics in finance. Guess what? The noise is the same. And this will not be a presentation on finance or on physics. I thought to work and to show you how physicists look at the financial markets as a lab. And to do so, I try to make a little investigation that will take you through the history of the models we use today in finance, their potential origins, and their miserable failures. Let's start a case. In 2008, we had a great crisis. All the most elegant models miserably failed. In 2008, not only banks have failed, but the models and the trust we had in those models failed. Because those models, they just failed to address the true complexity of the systems they were supposed to master. And we live in a world, particularly in finance, where we tend to believe the models that we have been studying. And anything that is not aligned with those models, we call it anomaly. In physics, anomaly means that a model is wrong. You need to think further. You need to robustify more your approach than just delegating with certitude what you do to your model. And so what happens in 2008, the system collapsed under the weight of the certitude the system had on their models. And this certitude, and the deterministic certitude about models, is something that physics has abandoned 200 years ago. Physics is not about exact science. Physics, or the true science, is about the culture of doubt. And what we can prove today, in whatever science, is the best explanation we may have so far. But it may be destroyed by new understanding. So we never convinced that our models represent the truth, but represent the best explanation we can give to that. But the most important thing is that we need to be aware of what our models are not able to master if you want to survive in this world. So now let's investigate how all this and all those certitudes may have took place through a different step in history, like through investigation. So let's start on the first act, 1982, the physics envy. What has happened towards the 19th century? The great success of thermodynamics and classical physics that was used in the Industrial Revolution to build engines, to build machineries, to explain how they work, how to make them more efficient. And actually, at that period, you have economists looking at physics model because they have something that was very attractive. Universality, invariant laws across different contexts, formal closure, they are consistent equations, and they can define operational variable that can be used in quantifying things. And so there you have someone like Irving Fisher, that was a student of Gibbs, and Gibbs is one of the father of the statistical mechanics in physics, that start to make some parallels. In physics and physical systems, you have a force, and the parallel he made is the marginal utility. Potential energy, like value. Market equilibrium, so in search for those equilibriums. I then wonder why the market moves every day if it is in equilibrium. Look, this is in an equilibrium. See? It's not as stable as wobbling around. Now it's in an equilibrium. And why the market moves every day? So it's not a stable one, at least. And then conservation laws. That may be budget constraints. But unfortunately, what he left behind is all the understanding of the complexity of the system in the market itself. Turbulence, phase transition, critical phenomena. The missing bits are the physics of the disorder. It just focuses on order, and it is the disorder that kills our portfolios, because markets are not steam machines. And then let's continue on that phase, because there is a second thing. 900, a bright student, Louis Bachelier, student of Poincaré. You know what he did? Someone knows Louis Bachelier? Yeah, he was the first one to be able to formalize how to value derivatives. Using what? Brownian motion. And how? 5 years before Einstein. You know what? Back then it was not adopted. The physics of randomness was in his way of valuing options, but the finance was not ready to listen. And then you fast forward 73 years, and this is the only equation I've put on the screen. This is the equation with which you value options, puts and calls, the Black-Scholes-Merton formula. 1973. Those who have done engineering may recognize the formula. It's the very same formula that Fourier, not in 1822, but in 1808, developed to describe the heat diffusion. How the heat, if you take a bar and you put a warm point in the middle, how the bar warms up through time. Just because the heat diffused with the same kind of noise, that is behind the noise, the random walk that generates the evolution of prices. So, you know what? Those gentlemen were able to understand that incertitude in prices have diffuse in the very same way like heat diffuse on material. And they were able out of it to price options. And it's fantastic because derivative market went from opaque to liquid overnight. Bam. So everyone starts using that. Oh, wait, we know how to price it. Oh, yeah, but then the volatility doesn't match. But don't worry, this is an anomaly. I will have invent the implied volatility because I have to do something, and I will start calibrating every day. But anyway, we have a price, and we can play around. Okay, but when you do this, and you forget that it's just an approximation of the real world, then you expose yourself at a huge risk. And the huge risk popped up. Bam. Black Monday. Oh, it was written Tuesday, but it was between Monday and Tuesday. It depends where you live in on the globe. We had a crash on the model in which we trust, we, not myself, but finance trust, should have occurred one every lifetime of the universe. But it happened on a Monday. So what does it mean? Well, probably I need to take care because I missed something in the equation. How many people lost their job in those days? How many of those that were trusting their models miserably failed like their models? So, in financial markets, like everything in nature, the extremes are not errors or anomaly and should be, forgot 16 days after it happens because the market memory, if you can calibrate it, is not longer than 16 days, at least the half-life time. They are structural property of the system. And when they happen, if you're not ready, while what you have been doing for months, years, has been working nicely, when they strike, they hurt you. But they are not anomalies. They are intrinsic property of the system. That's why when building the portfolios, when building investments, stop building certitudes, trying to be, aware that some extremes may happen because your model failed to describe the reality. Someone was saying that in whatever we do as human beings, all models are wrong because nature is infinitely more complex than what model can describe. Some of them are useful, even in AI, where you need to have a pinch of salt in applying them to be augmented by our model, not replaced by our model and believing in the model. It matters in physics as well, or in engineering, on everything. So what happens after 87? We had a sad and great event for finance. A sad event for physics. Because, today at CERN, we run the Large Hadron Collider, LHC, a CERN that has been directed by one of our compatriots, Fabiola Gianotti, a good friend of mine. And actually, they ran to investigate the origin of the universe, to rebuild the initial conditions of the Big Bang underground. But this project has started in the 80s. And in parallel in the United States and in Europe. But after the Cold War, the funding for physics dried up in America. And their version of the CERN's LHC was abandoned. So it was the superconducting supercollider. What it does, it let more than 900 physicists in search for something new to do. Guess what? They switch from particle detectors to Bloomberg terminal and float to Wall Street. And maybe I'm a little bit breadcrumb of that because around 1998, I was with a group of physicists because it's not only, if you like research, it's not only finding a job, like, putting your technical competencies at play in a bank. You still have the curiosity of a scientist. So you need to continue to do research, to continue to connect with universities. So what we did, in 1998. But we, understanding that there were a lot of physics in finance and markets could be considered as a lab of a natural system consisted not on free interacting particles, but free interacting brains. And the observables were the market indices. So why not trying to put together the best physics, I'm not part of those, and the best economics brains in order to build something together. And this is the birth of the Econophysics, which is something that has been around for centuries, as you have seen. But at least here it was formalized. And today we have PhDs in Econophysics at the Imperial College, at the Santa Fe Institute, at the MIT, at Max Planck Institute, people that study the complexity and how this complexity unfolds in the markets and how it can be used to understand to better, not perform essentially, but to create a better resilience and then not being exposed to drawbacks. Because drawbacks in finance kills you. Because we forget, particularly in portfolio allocation, the role of compounding. We remove the time variable from our portfolios because we make averages. If you make an efficient frontier, you are averaging out time, so the time disappears. So what happens if you repeatedly implement a portfolio? What is the role of the volatility of that? How many of you know that volatility is a drag or a tax you have to pay on long-term performances when you do compounding? Very few. And then if you have not only the Gaussian nicely distribution, but fat tails, this is what generates the short lifetime of managers, and then need to migrate and find other things to do. Yeah. So here I gave you some examples of people that successfully contributed to the field. And now the vindication, we are back to 2008. Armed with this different understanding and looking at that with the lenses of nature, 2008 was not a banking crisis. It was a phase transition. Water became ice suddenly. And this is something that can happen in systems that have the complexity, that is the complexity of the market, and by no means they can be considered simpler than the thin air around you. And some events or extreme events in our everyday life can happen and impact us. And so we do on risk management to try to avoid that. But this will not prevent us to take an airplane and to fly from A to B. Because in flying, for instance, everything is about prevention. But then you have the added value that in finance we call alpha, of rapidly flying from the point A to point B. But if you are not careful, then you crash. So in the real markets, what we have seen in 2008 is when the connectivity among different actors has been larger than a threshold, and the system undergone a phase transition. The state changed from liquid to solid. And now look at the future. I have a name of another friend that you may know, Professor Giorgio Parisi. He won a Nobel Prize in Physics in 2021, if I remember well. And Giorgio Parisi is another bright mind that contributed to analyze and study and formalize the physics of complexity in which markets are included, and had also participated to the Econophysics crowd. And actually, he was able to explain disordered systems that have not a single equilibrium, but a landscape of many stable or metastable states. Now, you are looking at me and say, what the hell is talking about? Okay, I give you an example. You remember the old TV that you have to find the right frequency to see the Rai 1, Rai 2? And sometimes, or probably in some particular location, probably in the country house and the older TVs, then you have the image, and you're looking at that, so very good image, and sometimes the screen started to do and coming back to the image. Unpredictable. It happens for some feedback loop in the electronic circuits, like we have feedback loop in our financial circuits, because there are the indices that we are the one that produce the evolution of the index, and we take decision on what we collectively decided. But this may generate metastable systems that describes avalanches, earthquakes, sand piles, intermittent systems that we call frustrated systems. And all those equilibria may persist all together, and eventually the system may flow in one side and another one. But it flows in a bad one while you're invested. Take care. So the system described by Giorgio Parisi wanders between trapped, released, and trapped again equilibria, or let's locally stable situations, and market is exactly the same thing. And so, looking at the future, what we have as Giorgio Parisi that explains spin glasses. Spin glasses are those magnetic systems that behave like the flock of birds. You know, look at those flock of birds and find the density of the flock of birds and measure it through time. You will see that you have something very close to the evolution market prices. Because we have, every one of us is one of those birds. And the market is the collective system. Most probably, Gaussian's explanations, the bell curve on which we base all our nice models, may locally work, maybe persistently for a bit of time, but when they spread apart, is something else at work. And then the same thing applies to finance. And the very same thing may apply to the AI that we have been talking today to explain how AI may converge out of complex systems to some usable solutions, but when also, it may also miserably fail. It hallucinates. So we have 3 different universes here, related by the same math, but not and the same uncertitudes. The noise, statistical noise, is a universal feature, but noise is not a wide thing that can just, you cannot consider because it's noise. It has its own structure, its own life, its own rules. If you forget them, the noise will kill you. And this is how finance and physics may be jointly cooperating in terms of finding, first of all, the understanding of the system. Secondly, helping to remove false certitude. Third, if one thing you may remain in your brain today, never trust your models. Never trust what is written in a book. Always address that in a very critical manner. Because models, books, whatever you see written is wrong if you believe that it's perfectly representing your everyday life. It's just something that will augment your capacity to take decisions. But who is accountable is not the model, it's you. It's your decision. And, well, let me conclude, but just to introduce myself at the end. So, as a speaker, I was a witness of all that, along with my dear friend, Paul. From 90 to 92, I was hunting exoplanets at the Observatory of Geneva. And incidentally, in the subset that I was studying, like a young student, I was a breadcrumb of that. My professors, Michel Mayer and Didier Queloz, they found the first exoplanet, a planet orbiting around another star than the sun, proving that solar systems are the rule rather than the exception. Every star you see in the sky have planets around. Today we have more than 4,500. And out of those studies, the two bright gentlemen with whom I had the pleasure to work a little bit, they won the Nobel Prize in 2019. Then I moved to CERN, smashing electrons for 10 years. And then I felt a little bit bored about the future of the present experiments in physics, in which in your research lifetime you have one experiment to do with 5,000 physicists working together and becoming an expert. And for you to know an expert is someone that knows everything about nothing. So they're very dangerous. So I didn't want to go there. And so in '98, I joined finance and Econophysics. Thank you very much. Oh, for you. Oh,
Thank you.
Sorry.
Gabriele Susinno.
There is, but for those of you, I just want to put the QR code. Who want to get in touch with me and eventually continue the discussion. I'll leave you the QR codes. If you scan it, it's my LinkedIn page.
Well, Gabriele Susinno, thank you so much. As we wait for the QR code to appear, just a quick one, because you described it, it was so fascinating to understand, you know, physics and finance, nature, and what we do with maths on the financial markets. But you just mentioned AI. And, you know, you told us about the epic failure of Elegant Model 2008, for example. What do you make of the impact that AI can do to create more sophisticated models and our capacity to understand the mechanism, the work of financial markets? Do you think this can help, or we have to be skeptical? You mentioned hallucination and all of that. But, you know, it will take just time for these mechanisms to get more efficient. As we saw, week by week, day by day, you know, they enhance the performance. What do you make of that?
You want me to make an elevator pitch on something that requires a week of discussion?
No, I'm sorry about that, but that's the way it works.
I'll do it. In AI, is not all equal. If I ask to every one of you to define what AI is, raise the hand who the one who is able to define me what is AI.
Yeah.
Exactly, because AI is a buzzword, a hype, embedding a large group of different algorithms. And now do not make the confusion between algorithms and model. First of all. Secondly, we confuse data and information. So AI is something that enables us to extract more information that we usually do from the set of data we have. So to come to your question, if we have more information, we may have been more efficient. But most probably, I don't think that an AI system would have prevented the majority of us to fall in the trap of believing in the same model and being caught by 2008. It will not do it. Because you need something human, the understanding of the weaknesses of the model, in which the AI is still a bit weak in that. Last thing, every one of us, we have models, so we do a parametric thing, we write an equation, this plus all the loading factors, then we go out and recalibrate, and we have one model. The nice thing probably of AI is that when you train the right algorithm on the right problem, then you are calibrating all the possible models together. How they are activated? With the data flow that you give every single day. But for this, we need to have a second session on the Parisi spin glasses.
Absolutely. Thank you so much again for this.